Hey everyone, welcome back to another build log of the DIYson lamp. I've been making some progress on my open source version of the Dyson light cycle, and I have some pretty exciting updates to share. Last time I managed to implement a drag chain based cable management solution that, while not as tidy as the original Dyson solution, does the job in a way that's affordable, easily reproducible at home using 3D printing, and is relatively discreet. This time, it's all about terminating that wiring with some electronics and lighting controls. Before I get into that, I just wanted to say thank you to all the people who have watched the video, specifically the last build log, who left a comment or subscribed to the channel in the last couple weeks. I started recording these videos because I quite literally thought that just one or two people would find it interesting, so knowing that it's resonating with you all is a really good feeling. Thank you for being here, it really means a lot to me. One of the questions I've left unanswered until now is how is the user interface of the lamp actually going to work? As a bare minimum, I need a way to cycle the power on and off, and also to control the brightness level. The real Dyson has a couple of additional features, advanced features like the ability to match ambient brightness and light temperature of the room, but I'm going to keep it simple for now and just stick with power and brightness, though I'm already investigating ways how I can add variable color temperature in future versions. Put simply, I need a hardware solution for talking to that code that I covered a few build logs ago that determines the brightness of the lamp. And I think I can do this with 3 buttons. One for toggling power, one for increasing brightness, and one for decreasing brightness. Like the original Dyson designers, I think the best place to put these controls is in the same general area as the LED itself, because this is where I'll typically be interacting with the lamp when positioning it. So intuitively, it just makes sense to me to put the controls right here as well. This placement has the added benefit of simplifying wiring since I'm already going to cram all of my electronics inside of this housing anyway. More on that later. Basic momentary buttons like this are an obvious, reliable, and affordable choice. And in most cases, the force required to depress the button is negligible. You wouldn't even think about it as a problem or a constraint, but here it poses a problem because the lamp's motion system is meant to move with just the slightest touch. And I spent a long time making sure that this was the case. And as a result, the amount of force needed to depress a mechanical button like this is more than enough to reposition the entire lamp. So for reliable one-handed operation, I'll need to find another solution. A better solution would be a button that has no resistance at all, say a capacitive button like this one, made by Adafruit. It's designed to operate just like a traditional clicky button, but the switch is triggered when tapped by a conductive object, like your fingertip, as opposed to a mechanical switch. These Adafruit ones are beautiful in their own right, but I've always envisioned these buttons sitting flush with the top of the LED cover, and I don't really see a straightforward way of mounting them so that we get that flush look. I chewed on this problem for a couple days, and then I remembered that at some point I had seen that Protopasta sells this specialty filament that's electrically conductive, and if it works like they say it does, that should mean that I could just 3D print some buttons in whatever shape and whatever form that I want, and use them to detect taps. I ordered this 50-gram sample of their electrically conductive composite PLA, and to my surprise, I had working 3D printed buttons within minutes. Well, it wasn't actually quite that easy. The version of the QT Py that I have, the RP2040, doesn't natively support capacitive buttons. So to make it work, I had to add resistors to each of the 3 pins, connecting them to ground. It turns out there's another QT Py model called the QT Py SAMD21, which functionally is, for my purposes, almost identical to the 2040, but it comes with native support for capacitive touch. So I went ahead and just made that upgrade. With the proof of concept for the capacitive buttons complete, now it's time to integrate them into the LED cover and ideally make them look good too. My original vision for this is that the buttons would just sit flush with the surface of the LED cover, almost like they're directly integrated into that part. My thinking here is that this would achieve a nice streamlined look, and it would mimic the minimalist nature of the original Dyson's controls. But after prototyping it out, I'm really second-guessing this concept. I definitely see a bit of that minimal aesthetic coming through, but there's just something off about it. I think the thing that's bothering me here is that, you know, when you're in a car, a newer car, where there's a console and it's made up of almost all capacitive buttons, in those situations, I often find myself fumbling around blindly, just pressing buttons accidentally, and in general, just having a really frustrating time. And in those situations, what I really want is just something physical and tactile, just a little bit of feedback so that I can, without looking, locate the button that I want and then press it. In my opinion, that's what's so great about old-fashioned knobs and mechanical buttons in cars, is that it enables this two-step process of orientation followed by interaction, where you can first probe in the general area of the button that you're looking for, and then once you found it, decide to interact with it. And I think that's what's missing here. And as tempting as it is to strip away visual noise and complexity, it's hard to justify that decision when it leads to a worse experience. So let's make sure that these steps happen in the right order. Orientation first, and then the choice to interact. With that in mind, in my next iteration, I added this raised perimeter around the outside of each button to act as kind of an orientation device. You can creep your finger along the surface of the LED cover, and by doing that, you'll know exactly where you are at all times without any accidental button presses. Outside of the usability benefits, there's also construction benefits too. So since these raised perimeters sit just above the surface of the LED cover, I have to make them into these independent little sockets, which are printed separately and then snap into place after the fact. This eliminates the overhang from the previous design and produces a much smoother and more consistent surface, and that means that the buttons and sockets are always going to slide perfectly into place and sit parallel to the cover surface. It's a small thing, but I think it really helps tidy up this area and make it look nice, neat, and intentional. These buttons are pointless if they don't control anything, so let's switch gears to electronics. First off, I have some new components. In trying to cram all the LED electronics into this tiny housing, it was immediately obvious that this LED power supply was just way too big. Finding a smaller LED driver was pretty easy, but it broke compatibility with my LED, so I had to take a step back, do that cabbage, rabbit, fox riddle a bit more, until I found an LED that was compatible with the driver and an LED holder that was compatible with the LED. And with those in place, I can finally move on to the fun part, which is that I made a PCB. My first PCB. I didn't really think that it would come to this, but overall I just wasn't satisfied with the attempts that I was making to cram all these components into the LED cover. If any of you have done a project like this, you know that simple things like wires that seem small on the surface can take up a lot of space once you try to wire all your components together, and space is so limited in here that every square millimeter counts. And fitting everything onto a custom PCB saves me a ton of volume, and I can just cram everything in here in a really tidy way. And this is my PCB, and on top there's the QT Py for controlling the brightness, the LED driver sits next to it, and there's a buck converter which powers the QT Py. I also added a little diode which makes sure that the 5 volts coming from the buck converter into the QT Py only goes in one direction. On the back, I have 3 pogo pins which are aligned perfectly with the capacitive buttons that sit on the top of the cover. This ensures that there's constant contact with the capacitive buttons, but I don't have to permanently attach those buttons to the PCB. I'm really satisfied with how this PCB turned out. I was initially really intimidated by the prospect of designing a PCB, so pulling this off feels like a bit of a personal milestone, and weirdly it was both harder and easier than I imagined. I want to call out this guide that I found on Adafruit, which in my opinion is a perfect introduction to both the theory and execution of designing a PCB. I'll leave a link in the description for those that want to break into this, and I'd really recommend doing so if you have a project that could benefit from it. I seriously can't recommend it enough. Alright, back to the lamp, and it's time to mount the loaded up PCB into the LED cover. These 3 holes are used to mount the board in this little recess, and it's all held in place by 3 M1 panhead screws, which are screwed directly into the plastic of the LED cover. The final touches are a little strain relief clip for the power cable, and finally one more drag chain termination piece to tie everything together. And now, finally, it's time to power on the lamp for the first time, a momentous eventuality that has pervaded the consciousness of at least several people for over... It flickers. Fortunately, this only appears on camera, and double fortunately, it does seem like the PCB is working correctly. But yeah, this flickering is really bad, and I can't use this lamp on camera if it continues to do this. To be totally transparent, I have known about this problem for a while. The flicker only appears on camera, so I didn't notice until I started shooting the electronics portion of this very video. My first instinct was just to eliminate the flicker by increasing the PWM frequency. This LED driver is already maxing out at 1 kHz, which is its maximum frequency, so I had to do some careful overclocking, but after that was done, I quickly went into the code and cranked the frequency up to 4000 Hz. Where mercifully the flickering stopped. And that's where the whining started. It turns out that pushing the PWM frequency beyond the stated maximum, even if you overclock it, introduces a high-pitched whine that, by the time you get to 4 kHz, is audible from a few feet away. So that's the dilemma I'm faced with right now. Do I keep the frequency low and deal with the on-camera flickering, or eliminate the flickering by introducing the whine? To be honest, I don't think either way are really acceptable for the final version, and I'm a little stumped with what to do here. My only concrete path forward right now involves swapping this for a driver that has analog dimming, but that comes with its own challenges. Because electronics is a real weak point for me, if there's anyone out there who's willing to lend their expertise, please leave a comment so we can chat a little bit more on Discord. I would really appreciate some expert advice on this one. For now though, for your sake, I'm going to choose the less visually objectionable option and leave the frequency overclocked, and I'll spare you from the whine. Alright, I'll keep dealing with this, I'll find a solution, but let's move on to some other updates. Down at the base of the lamp, I integrated a drag chain termination clip into the base adapter. This clip is really similar to the one that we saw on the LED cover, and it just functions to hold the drag chain in place and give the cable a safe exit route. While we're down here, I've also started working on how to make the transition from this dynamic part of the lamp down to the static base. I could just leave enough exposed slack that would allow the lamp to turn a full 360 degrees, but if you watched any of my last build logs, you know that I rarely settle for the first solution. So I want to find a more elegant solution to completely hide this transition into the base. I think one way that we could do that is using what's called a slip ring. I've never used one of these before, so I picked up a couple of cheap ones just to play around with and see how they work. And I've already started working on a couple of prototypes using this really tiny slip ring, but I want to work some kinks out before I share it in more detail, but I think it's going to be really cool once it's done. Some small improvements to the code include a smooth transition between any change in brightness. So when you power the lamp on, it will fade from off to the last brightness value, and when you change brightness, it is a smooth transition from the current brightness to the desired brightness. Lastly, I finally got a usable part back from Shapeways, who I was using to fabricate this little metal adapter that holds the LED against the heat pipe and then gets fastened to the end of the arm. While this part works, it has taken me months and many iterations to get it right. Warping and shrinking issues that arose from the manufacturing process have made this little component a bit of a nightmare, and I wouldn't feel good about asking anyone else to roll the dice with their own money to order this part for themselves. Instead, what I plan to do is redesign this part with CNC machining in mind, and then hopefully find a way to manufacture it cheaply and get it out to people who want it. I need this part to be strong, heat resistant, and ideally thermally conductive, so if I can get this part affordably CNC'd out of aluminum, I think that'd be a much more preferable option. I'll come back to this part in the future build log and I'll let you know what I'm up to. Alright, I think that pretty much wraps up my progress so far. I have some really interesting, exciting, challenging improvements in mind for the next build log, so I really hope you'll come back for that one. Until then, thank you so much for watching, Happy New Year, and I'll see you in the next build log. See ya!